The universe began in a flash of light and energy too hot to imagine. We are about to compress its entire 13.8 billion year story into one thrilling 2-minute journey. You will witness the birth of stars, the rise and fall of dinosaurs, and the entire human saga in the blink of a cosmic eye. How did everything we know come from a single point of infinite density? What strange forces will ultimately decide the fate of all existence? By the end of this ride, you will see your own life and every human story as part of a single breathtaking cosmic epic. Are you ready to see where we fit in the grand story of everything? Our story starts with everything, every single atom and galaxy, crushed into a point of infinite density and heat. This is the singularity, a state so extreme our laws of physics simply break down. Then, in an event we call the Big Bang, reality itself began to expand. But this was not a slow unfurling. In the tiniest fraction of a second, the universe underwent a period of inflation, ballooning from smaller than a single proton to the size of a grapefruit faster than light could travel across it. Imagine the most powerful explosion you can conceive, then multiply its energy by a number with more zeros than stars in the sky. That raw energy began to cool, just enough for the fundamental forces of nature to separate from their unified state. Gravity, the strong nuclear force, the weak force, and electromagnetism each took on their own unique roles, setting the stage for everything to come. In this searing hot soup, the first particles flickered into existence, quarks and electrons dancing in a blinding plasma of light. For several 100,000 years, the universe remained this way, an opaque, roiling fog of energy where not a single photon could travel in a straight line. It was a cosmic dawn waiting for its first clear sunrise. For hundreds of thousands of years, the universe remained a hot, featureless fog. It was a sea of hydrogen and helium gas so thick that light could not travel freely. This was the cosmic dark ages, a profound silence stretching for millions upon millions of years. In that vast, unlit expanse, gravity was the only sculptor, slowly pulling the faintest wisps of gas together. Within these dark, collapsing clouds, something miraculous began. Hydrogen atoms, squeezed together by immense pressure, started to fuse. Deep in the hearts of these primordial clouds, the first nuclear furnaces ignited. The very first stars were born. They were not like our sun. These were behemoths, monsters hundreds of times more massive, burning with a ferocious blue-white intensity. Their light was the universe's first true sunrise. This ultraviolet radiation from the first stars and the earliest galaxies blasted through the surrounding fog. It ripped electrons from the neutral hydrogen atoms, reionizing the gas and clearing the cosmic haze. The universe, for the first time, became transparent. Light could finally travel across the cosmos. We call this moment the cosmic dawn, the end of darkness and the beginning of the universe we can see. These first brilliant stars did not live in solitude. They were the seeds of something far grander. As gravity continued its relentless work, it wove the fabric of the cosmos into a vast, intricate structure known as the cosmic web. Picture an unimaginably large spider's web, with shimmering strands of dark matter and gas stretching across billions of light years. Where these strands intersected, matter pooled into dense knots. These were the nurseries for the first galaxies. Galaxies are the cities of the cosmos, each one a colossal island containing hundreds of billions of stars. They come in majestic forms. Spiral galaxies like our own Milky Way are graceful pinwheels with sweeping arms of young blue stars. Elliptical galaxies are older, smoother spheres of reddish stars, the quiet giants of the universe. And then there are the irregular galaxies, chaotic and misshapen, often bearing the scars of violent encounters, because the early universe was a crowded, dynamic place. Galaxies did not form in peace. They crashed together in titanic mergers, events so powerful they could warp the very shape of a galaxy. and trigger the birth of millions of new stars in brilliant starburst fireworks. At the heart of nearly every large galaxy, including our own, lies one of the universe's most mysterious objects, a supermassive black hole. These are not the monsters that destroy, but the silent anchors that shape. Their immense gravity governs the orbits of stars at the galactic core, and when they feed on surrounding gas, they can become quasars, outshining entire galaxies with their ferocious energy. This era of cosmic construction, of weaving webs and building galactic empires, set the large-scale architecture of the universe for all time. It was a period of breathtaking violence and equally breathtaking beauty, painting the darkness with the first enduring structures of light. Deep within those vast galactic cities, the true magic of creation happened on a smaller, more intimate scale. Inside colossal clouds of gas and dust called nebulae, gravity's patient work continued. These stellar nurseries are the most beautiful places in the cosmos, glowing with ethereal colors from the radiation of nearby stars. Here, a slight disturbance, perhaps the shock wave from a distant supernova, can cause a dense knot within the cloud to begin collapsing under its own weight. As it spins and contracts, it forms a hot, dense core called a protostar. For hundreds of thousands of years, this young object gathers more material, growing hotter and hotter at its center until the pressure and temperature become unimaginable. At about 15 million degrees Celsius, hydrogen nuclei finally overcome their mutual repulsion and begin to fuse into helium. In that instant, a star is born. Nuclear fusion ignites, releasing a torrent of energy that pushes outward, halting the star's collapse. A new sun switches on in the darkness, but the story does not end there. Around this newborn star, the leftover gas and dust swirl in a vast, flat disk. This is the protoplanetary disk, a cosmic construction zone. Within this disk, microscopic particles of dust and ice begin to stick together, colliding and merging over millions of years. These clumps grow into pebbles, then boulders, and finally into planetary embryos. In the hot inner disk, only rock and metal can survive, forming the seeds of small, rocky worlds like Earth. Farther out, where it is cooler, vast amounts of ice and gas accumulate, creating the cores of giant planets like Jupiter. The remaining debris becomes asteroids and comets, the leftover building blocks of a solar system. We have seen this process captured in stunning detail by telescopes like Hubble and the James Webb Space Telescope. Their images show these glowing disks, these celestial nurseries, around young stars in our own galaxy, proving that planet formation is not a rare event but a common chapter in the life of a star. Our own solar system began this exact same way, 4.6 billion years ago, in just such a cloud. Every planet, every asteroid, and every one of us was forged in the heart of a nebula and assembled in the disk around a newborn star. Our own solar system was born from such a swirling disk of gas and dust. As our young sun ignited at the center, its fierce solar wind began to blast the lighter gases, hydrogen and helium, out toward the colder outer reaches. This created a fundamental divide in our cosmic neighborhood. In the hot, turbulent region close to the sun, only the tough, refractory materials could survive the heat. Metals like iron and nickel and rocky silicates clung together. These particles collided and stuck over and over in a process called accretion. They grew from dust grains to pebbles, then to mountain-sized bodies called planetesimals. For millions of years, these planetesimals smashed into each other in a chaotic, violent dance of creation and destruction. The winners of these collisions grew larger, their gravity pulling in more and more material, eventually sweeping their orbits clear to become the rocky, dense worlds we know as Mercury, Venus, Earth, and Mars. Farther out, beyond what we call the frost line, it was cold enough for volatile ices like water, ammonia, and methane to freeze solid. Here, the process of accretion had a colossal head start. These icy planetesimals could grow much larger, and once they reached about 10 times the mass of Earth, their gravity became powerful enough to rapidly capture the vast amounts of hydrogen and helium gas still lingering in the disk. This is how the gas giants Jupiter and Saturn were born, becoming the solar system's gravitational kings. Their immense presence shaped everything that followed. Between Mars and Jupiter, the gravitational tug-of-war with the newborn Jupiter prevented another planet from forming, leaving a belt of scattered remnants, the asteroid belt. Even farther out beyond Neptune, a vast disk of icy bodies was left over, a frozen archive of the solar system's earliest days known as the Kuiper belt. But the young solar system was not a peaceful place. For hundreds of millions of years after the planets formed, a period we call the Late Heavy Bombardment, the inner worlds were pummeled by a relentless rain of leftover planetesimals and asteroids. The surfaces of the Moon, Mercury, and Mars still bear the cratered scars of this ancient cosmic violence. For Earth, this bombardment may have been a delivery service, bringing not just destruction, but also the water and complex organic molecules that would one day become the essential ingredients for life. For Earth, that violent bombardment was a crucible of creation. Our world began as a molten sphere of rock, its surface a churning ocean of magma under a sky filled with falling fire. There was no water, no air, just a searing inferno constantly reshaped by cataclysmic impacts. Then came the blow that defined our planet's destiny, a wandering world roughly the size of Mars and named Theia by scientists slammed into the young Earth. The collision was so unimaginably violent it would have vaporized rock and metal, merging the two bodies into one and blasting a titanic plume of vaporized debris into orbit around our planet. In the cooling aftermath, this swirling ring of incandescent material began to clump together, drawn by its own gravity. Within perhaps just a single century, this debris coalesced into a single spherical body. Our Moon was born. This catastrophic birth gave Earth gifts essential for life. The impact likely set our planet spinning at a stable tilt, that 23.5-degree angle responsible for our predictable seasons. And as the newborn Moon cooled and settled into its orbit, its gravitational pull began to sculpt the oceans, creating the rhythmic tides that would later stir the primordial soup and shape coastlines. From a hellish collision came a companion world, a climate regulator, and the pulse of our oceans, setting the stage for everything that followed. The fiery chaos of Earth's youth could not last forever. As the bombardment slowed, our planet began its long, slow cooling. Steam from countless volcanic eruptions condensed in the cooler upper atmosphere and fell back to the scorched surface as rain, a deluge that lasted for millions of years. These rains filled the low basins, carving the first river valleys and pooling into vast global oceans. Earth was now a water world, with only scattered volcanic islands breaking the surface of a warm, chemically rich sea. And in that sea, somewhere, the universe performed its greatest magic trick. From non-living matter, life emerged. We do not yet know exactly how it happened. Perhaps it began in the sunlit shallows, a primordial soup energized by lightning strikes. Or maybe it sparked in the total darkness of deep-sea hydrothermal vents, where mineral-rich water gushed from the crust, providing both energy and a rich chemical buffet. In one of these environments, simple organic molecules began to link together into more complex chains. They formed microscopic bubbles that could trap chemicals inside, creating the first crude cells. These were the first living things, simple prokaryotic organisms, little more than a protective membrane and a strand of genetic material. They fed on the chemicals around them in a world with no oxygen. For 2 billion years, this was life on Earth, a silent, microscopic world thriving in the dark and in the deep. Then, one of these simple cells made a revolutionary discovery. It evolved a way to capture energy directly from sunlight. This process, photosynthesis, used the sun's power to turn water and carbon dioxide into food, releasing a waste product that was utterly toxic to almost every other living thing on the planet: oxygen. At first, this oxygen was quickly absorbed by iron in the oceans, rusting the seas and sinking to the bottom to form banded iron formations we mine today. But eventually, the seas could absorb no more. Oxygen began to bubble out into the atmosphere. This was the Great Oxidation Event, a planetary catastrophe for the life that existed. For the anaerobic organisms that had ruled the Earth for so long, this was a poison gas causing a mass extinction, but it was also the key to a more complex future. This new, oxygen-rich atmosphere allowed for more efficient energy use and eventually led to the development of cells with a nucleus, eukaryotes, the building blocks of all complex life to come. The stage once set by geology and chemistry was now firmly in the hands of biology. For billions of years, life on Earth remained a microscopic world, a patient and quiet prelude. Then evolution discovered size and scale. The planet entered the Mesozoic era, a period spanning over 180 million years, often called the Age of Reptiles. This was the world of giants. On land, dinosaurs evolved into an astonishing array of forms, from the towering, long-necked sauropods that shook the ground with their steps to the nimble, razor-clawed predators that hunted in packs. The skies, once empty, were conquered by the pterosaurs, leathery winged reptiles with wingspans rivaling small airplanes. In the oceans, another group of reptiles, like the long-necked plesiosaurs and the monstrous mosasaurs, became the apex predators of the deep. This was an era of spectacular biodiversity, a world ruled by creatures of immense power and strange beauty, but the stage they walked upon was not static. Beneath their feet, the very ground was on the move. The Earth's crust is broken into massive, interlocking plates that float on the semi-fluid mantle below. This process, plate tectonics, is the engine that reshapes our planet. At the dawn of the Mesozoic, all the world's landmasses were joined into one supercontinent, a colossal island called Pangaea. As the Mesozoic unfolded, the immense heat from Earth's core caused this supercontinent to slowly, inexorably, tear itself apart. Rifts became inland seas, and seas became vast oceans. North America peeled away from Europe, South America split from Africa, and India began its long, lonely journey northward. This continental drift did more than just change the map. It created new coastlines, new mountain ranges, and most importantly, new climates. The unified, dry interior of Pangaea gave way to separated continents with distinct weather patterns, creating isolated ecosystems where evolution could experiment in new directions. Lush forests spread and coastlines teemed with life. The breaking apart of the world was the very reason for its incredible biological richness. For over 160 million years, these magnificent creatures adapted and thrived in this changing world, their dominance seeming absolute and eternal. But the universe, as we have seen, has a way of introducing sudden, decisive change. Their reign ended not with a whimper, but with a cataclysm from the stars. 66 million years ago, a mountain-sized asteroid, a piece of cosmic debris left over from the solar system's violent construction, found Earth in its path. This was the Chicxulub impactor, a rock roughly 6 miles wide, traveling at over 45,000 miles per hour. The moment it struck the shallow seas of what is now Mexico's Yucatan Peninsula, it released energy equivalent to billions of atomic bombs. The atmosphere itself was torn open. The immediate effects were apocalyptic. The kinetic energy of the impact was instantly converted into heat, ignoring a global firestorm. Wildfires raged across continents, incinerating forests and turning the sky into a blanket of ash. In the ocean, the impact triggered tsunamis over a mile high that scoured coastlines thousands of miles away. But the true killer was what happened next. The impact vaporized billions of tons of rock, launching it high above the atmosphere. This pulverized debris, along with soot from the global fires, formed a thick shroud of dust that encircled the entire planet. It blotted out the sun. For months, perhaps years, the world was plunged into a profound darkness and a deep, chilling cold. This was the impact winter. Photosynthesis ground to a halt, plants withered and died. The great herbivores with nothing left to eat starved, and the mighty predators that hunted them soon followed. It was a planet-wide reset button pressed in a single, terrible day. In the ashes of that ancient world, however, opportunity stirred. The mammals that survived were not the kings of the age. They were small, shrew-like creatures that lived in burrows, emerging at night to scavenge insects and seeds. Their small size, their fur for warmth, and their varied diets became their salvation. While the giants perished in the cold and dark, these humble survivors endured. With the dominant reptiles gone, the ecological throne was empty. Over the millions of years that followed, these mammals cautiously emerged from the shadows. Freed from the constant threat of dinosaur predators, they began to explore new ways of life. They grew larger, diversified into countless new forms, and eventually took to the trees, to the skies, and back to the seas. One cosmic accident, a random strike in a vast solar system, erased one world and gifted us another. From those dark, quiet burrows, a new world slowly emerged. This was the Cenozoic era, the age of mammals, a 66-million-year story of recovery and spectacular reinvention. With the dinosaurs gone, those small, surviving creatures found themselves on an empty stage, and evolution began to experiment with breathtaking speed. From humble, insect-eating ancestors, mammals exploded into an astonishing diversity of forms. Some grew massive, like the woolly mammoths and saber-toothed cats that would later rule the ice ages. Others took to the skies, evolving the complex wing structure of bats. Many returned to the seas, their bodies streamlining into the shapes of whales and dolphins. But one particular branch of this mammalian family tree took a different, quieter path, a path that would ultimately lead to us. This was the primate lineage. The earliest primates were small, tree-dwelling creatures that looked somewhat like modern-day lemurs or tarsiers. Life in the dense canopy presented unique challenges and opportunities, and evolution equipped them with a revolutionary set of tools. To navigate a complex three-dimensional world of branches, they evolved grasping hands with opposable thumbs, allowing for a secure grip. Their eyes migrated to the front of their faces, providing overlapping fields of vision. This depth perception was a survival superpower, letting them judge precise distances for leaping between branches. These were not just physical changes, they were cognitive ones. Navigating the arboreal maze required better memory, sharper senses, and more complex social coordination to find food and avoid predators. Over tens of millions of years, these early primates diversified. Some remained in the smaller, nocturnal niche, while others grew larger and became active during the day. From these diurnal groups emerged the ancestors of monkeys and later the apes. The first true apes appeared in the lush forests of Africa and Eurasia around 25 million years ago. They were larger than monkeys with no tails and possessed even greater shoulder mobility for swinging through the trees, a method of movement called brachiation. They lived in complex social groups, their intelligence deepening with the demands of their environment and their interactions with each other. One of these ape lineages, weathering shifting climates and changing landscapes, would eventually give rise to a group we call the hominids, the great apes that include orangutans, gorillas, chimpanzees, and ourselves. Every adaptation, from that first grasping hand to those forward-facing eyes observing the world from a high branch, was a silent step in a journey that was, without any plan or purpose, writing the opening chapters of the human story. The story of us begins not in a grand city, but on the sun-baked grasslands of ancient Africa. Here, a crucial divergence occurred. One lineage of apes began to spend more time on the ground, and over millions of years, their skeletons slowly transformed. The most famous evidence of this change is a 3.2-million-year-old skeleton nicknamed Lucy, a member of the species Australopithecus afarensis. Lucy's bones tell a revolutionary tale. Her knee joints and the shape of her pelvis show she walked upright, a trait called bipedalism. This was our first great evolutionary leap. Walking on 2 feet freed the hands for other tasks, lifted the eyes higher to see over tall grass for predators or prey, and was more energy efficient for covering long distances. But Lucy's brain was still quite small, not much larger than a chimpanzee's. She and her kind were not yet human, but they had taken the first earth-shaking step. The next chapter is written in stone, literally. Around 2.4 million years ago, a new genus appears in the fossil record, Homo, meaning man. The earliest known species is Homo habilis, the handyman. What defines them is not a dramatic change in body, but in behavior. We find their campsites littered with simple, sharp stone flakes and crude chopping tools. These were the world's first technology, crafted by deliberately striking one rock against another to create a cutting edge. This was a cognitive revolution. It required foresight, an understanding of geometry and force, and the ability to teach the skill to others. With simple tools, Homo habilis could process meat and marrow from scavenged carcasses, accessing a richer, more reliable food source. A better diet fueled a larger brain, and a larger brain demanded more energy, creating a powerful feedback loop of innovation and biological change. Then came a true pioneer, Homo erectus, the upright man. Appearing around 2 million years ago, this species looked far more like us. They were taller, with bodies built for endurance running. Their brains were significantly larger, and they were the first hominins we know to master a force that would reshape the world: fire. Evidence from sites in Kenya and South Africa shows they could contain and control flames. Fire provided warmth, allowing them to venture into colder climates. It offered protection from nocturnal predators, turning the darkness from a time of terror into a time of social gathering. Most importantly, fire cooked food. Cooking breaks down tough fibers and makes nutrients more available, supercharging calorie intake and further fueling that growing brain. With these advantages, Homo erectus did something no ancestor had ever done. They walked out of Africa. Their fossils are found from the Republic of Georgia all the way to Indonesia. They were the first global explorers, adapting to deserts, forests, and temperate plains, a testament to their incredible ingenuity and resilience. Their success lasted for nearly 2 million years, a span of time that makes all of recorded human history seem like a single afternoon. This entire journey was not a solitary one. Each step forward was built on social cooperation. Bipedal hunters on the savannah would have been vulnerable alone, but in groups they could watch for danger and coordinate to scavenge or hunt. Making and using tools is a social skill, passed from one generation to the next through observation and mimicry. Controlling fire required a collective effort to gather fuel and tend the flames through the night. The archaeological record shows them living in base camps, places to return to share food, and to raise their young. This social fabric, woven from communication, shared purpose, and care for one another, was the invisible scaffold upon which our intelligence was built. Our brains did not expand simply to solve physics puzzles about stone tools, but to navigate the infinitely more complex puzzle of other minds, to build trust, to forge alliances, and to tell the stories that would bind a group together. The path from Lucy's first steps to the global migrations of Homo erectus was paved not by lone geniuses, but by communities learning together how to survive a changing world. Yet the world of Homo erectus was not ours. For over 1 million years, they shared the planet with other human species, a family tree with many branches. Then, somewhere in Africa between 300,000 and 200,000 years ago, a new branch emerged, anatomically modern Homo sapiens. We looked like them, but for tens of thousands of years, our behavior was not dramatically different. We made the same kinds of stone tools, lived in similar social groups, and showed little sign of what was to come. Then, around 70,000 years ago, something extraordinary happened. Something clicked in the human mind. This is the cognitive revolution, a sudden leap in our ability to think, communicate, and imagine that changed everything. The most likely catalyst was the development of complex, flexible language. Before this, communication was likely limited to practical warnings like a grunt for danger. But now, language evolved into something far more powerful. It became a tool for gossip, for building social bonds and trust within larger groups. It allowed for the sharing of detailed plans for a hunt or the precise location of a water source. Most importantly, it enabled us to talk about things that do not exist. We could speak of spirits, of ancestors, of future hopes and past legends. With this new language, we gained the ability to create and believe in shared fictions. These fictions, these stories, are the foundation of all human culture. They allowed hundreds, even thousands of strangers to cooperate around a common belief, be it a tribal identity, a religious faith, or the value of a carved shell. The evidence for this revolution is not in our bones, but in the artifacts we left behind. Suddenly, we see beads made from shells and animal teeth, carefully pierced and worn as personal adornment. This is not practical, it is symbolic. A bead says, I am part of this group, or I have status. We find the earliest musical instruments, flutes carved from bird bone. We see the breathtaking birth of art on the walls of deep caves like Chauvet in France. These are not simple sketches. They are masterpieces of observation and technique, depicting lions, rhinoceroses, and horses with a vitality that feels immediate even after 30,000 years. This art was likely part of complex rituals, a way to connect with the spiritual world or to pass down knowledge. This cognitive toolkit, this ability to live in a dual reality of trees and rivers and also of gods and nations, gave Homo sapiens an unprecedented advantage. When we migrated out of Africa and encountered our robust, intelligent cousins, the Neanderthals, we did not outcompete them with brute strength. They were stronger and their brains were just as large. We outcompeted them with our flexible social networks, our superior planning, and our capacity for innovation. We could form larger, more cooperative bands, share information across wider distances, and adapt to new environments with startling speed. Within a relatively short time, in geological terms, we were the last human species standing. Not because we were the strongest, but because we were the best storytellers, the most connected, and the only ones who could look at a painted bison on a cave wall and see more than just pigment and rock. That storytelling mind was about to reshape the very planet. For nearly 200,000 years, our ancestors lived as nomadic hunter-gatherers, following the migrations of animals and the seasonal ripening of wild plants. Their world was one of constant movement, intimate knowledge of the land, and small, flexible social groups. Then, beginning around 12,000 years ago, in a few fertile regions of the globe, something shifted. It started with a simple observation. People noticed that seeds from certain wild grasses, if scattered on the ground, would sprout into new plants. They began to deliberately save the best seeds and plant them in cleared areas. This was the birth of agriculture, a slow-motion revolution that would change everything. In the same regions, wolves that lingered near human camps gradually became dogs. Wild goats, sheep, pigs, and cattle were also slowly brought under human control through selective breeding, a process we call domestication. These animals provided not just meat, but also milk, wool, and muscle power. This was not a sudden invention, but a gradual, mutual adaptation. The plants and animals evolved to depend on human care, and humans evolved a new way of life to care for them. The consequences were profound and irreversible. Farming produced a food surplus. For the first time in human history, not everyone had to spend every day searching for something to eat. This surplus allowed populations to grow and settle permanently in one place. The first villages appeared, clusters of mud brick houses along fertile river valleys. With settlement came new problems and new inventions. How do you store a grain surplus? The answer was pottery. How do you divide up land and property? This led to the first systems of measurement and eventually written records. How do you organize labor to build irrigation canals to water the fields? This required leadership and social hierarchy. The village grew into the town, and the town, in some special places, blossomed into something entirely new, a civilization. These first cradles of civilization emerged independently in 4 great river valleys where the soil was rich and water was reliable. In Mesopotamia, the land between the Tigris and Euphrates rivers, the Sumerians built the world's first cities like Uruk and Ur. They invented the wheel, the plow, and most importantly, writing. Their cuneiform script pressed into clay tablets began as simple accounting marks to track barley and sheep, but soon evolved to record laws like the famous Code of Hammurabi and epic poetry like the Tale of Gilgamesh. In Egypt, the predictable flooding of the Nile River created a narrow strip of lush black land amidst a desert. Here, a powerful, godlike pharaoh commanded the labor of thousands to build monumental tombs, the pyramids, which were not just graves but cosmic machines designed to launch a king's soul to the stars. In the Indus Valley, in modern-day Pakistan and India, cities like Mohenjo-Daro were marvels of urban planning with straight, grid-like streets, sophisticated drainage systems, and large public baths, suggesting a society obsessed with cleanliness and order. And in China, along the Yellow River, early dynasties like the Shang mastered bronze casting on a colossal scale and left behind oracle bones, the earliest evidence of Chinese writing, used to communicate with ancestors and divine the future. Each of these civilizations, separated by vast deserts and mountains, somehow arrived at the same revolutionary ideas: cities, writing, kings, and temples. They looked to the heavens and created calendars to track the seasons for planting. They studied the stars and mapped constellations, seeing the patterns of gods and heroes. They pooled their collective labor to raise structures so immense they were meant to echo eternally, declaring humanity's newfound power to leave a permanent mark on the world. The quiet life of the nomadic band was gone, replaced by the bustling, noisy, creative, and often unequal world of the city-state. Humanity had tied its fate to the land, and in doing so, launched itself on a trajectory of accelerating change that would soon connect these once isolated river valleys into a single, intertwined story. From those first river valleys, the human experiment in civilization began to spread and collide. The story accelerates, becoming a tapestry woven from the threads of empires, ideas, and iron. In the West, the city-states of Greece gave the world democracy in Athens and militaristic discipline in Sparta, but their greatest export was a way of thinking. Greek philosophers like Socrates, Plato, and Aristotle asked fundamental questions about reality, ethics, and knowledge, laying the intellectual foundation for the Western world. Meanwhile, in the East, the teachings of Confucius in China and the Buddha in India offered profound systems for moral living and spiritual enlightenment, philosophies that would shape Asian civilizations for millennia. These were not isolated developments. The Persian Empire, a colossal administration stretching from the Indus River to the Aegean Sea, built the Royal Road, an ancient highway system that connected distant provinces and facilitated the exchange of goods and ideas across continents. Then came Rome. What began as a small settlement on the Tiber River grew, through relentless organization and military might, into an empire that encircled the Mediterranean Sea, a mare nostrum, our sea. The Romans were master engineers, gifting the future with paved roads that still underpin European highways, aqueducts that carried water across vast distances, and monumental arenas like the Colosseum, where the drama of life and death played out for the masses. Their system of law became the bedrock of legal thought across the Western world. Yet all empires contain the seeds of their own dissolution. Rome's vast borders became impossible to defend, its economy strained, and its political center could not hold. By the 5th century, the Western Roman Empire had fragmented, leaving a power vacuum across Europe. This ushered in what was once called the Dark Ages, but we now see as a period of profound transformation, not mere darkness. In the East, the Roman Empire continued for another 1,000 years as the Byzantine Empire, a Christian bulwark preserving ancient knowledge, and in the Arabian Peninsula, a new force was rising. In the 7th century, the revelations of the Prophet Muhammad gave birth to Islam. This new faith spread with astonishing speed, creating an Islamic civilization that stretched from Spain to the borders of India. This was the Islamic Golden Age. While much of Europe was politically fractured, scholars in Baghdad, Cairo, and Cordoba were not preserving knowledge, they were expanding it. They built upon the works of the Greeks, Persians, and Indians, making staggering advances in mathematics, giving us algebra and the numeral system we use today, including the concept of zero. Their astronomers mapped the stars with refined instruments. Their physicians like Ibn Sina wrote medical texts that would be standard in Europe for centuries, and their philosophers wrestled with faith and reason. This was a true crossroad of the world, where Jewish, Christian, and Muslim thinkers worked side by side in houses of wisdom, translating and debating. Back in Europe, a new order was slowly coalescing from the ruins of Rome. This was the Middle Ages, a time defined by feudalism, a decentralized system of loyalty and land, and by the towering power of the Christian Church. Kings were crowned by popes, and faith was the glue of society. This era saw its own majestic innovations, not in sprawling empires, but in stone and spirit. Across the continent, communities pooled their resources and their devotion for generations to build Gothic cathedrals. These were not just churches, they were stone prayers reaching for the heavens, their stained glass windows filtering divine light, their soaring vaults demonstrating a mastery of architecture that still inspires awe. This was also the age of knights and castles, of chivalric codes and epic poems, of Viking longships and the sprawling trade networks of the Silk Road, which tenuously connected the markets of Europe with the splendors of China, still under the enduring influence of dynasties like the Han and the later Tang. It was a millennium of immense contrast, of brutal conflict and breathtaking beauty, of isolated manners and cosmopolitan cities. Through conquest, trade, and pilgrimage, technologies like the stirrup, the heavy plow, and the windmill spread, slowly increasing productivity and changing daily life. The compass, paper, and gunpowder, inventions from China, began their slow, world-altering journey west. This entire period, from the forums of Rome to the scriptoriums of monasteries and the bustling souks of Baghdad, was a vast, messy, and indispensable chapter in the human story, a necessary fermentation of ideas and identities that was quietly setting the stage for the next great explosion. The quiet ferment of the Middle Ages gave way to an explosion of light. A spirit of restless inquiry began to stir across Europe, a movement we call the Renaissance, meaning rebirth. It was a rediscovery of the classical knowledge preserved by Islamic scholars and Byzantine scribes, now fueling a new confidence in human potential. In Florence and Rome, artists like Leonardo da Vinci and Michelangelo were no longer seen as mere craftsmen, but as geniuses. Da Vinci's notebooks reveal a mind that saw no boundary between art and science, sketching flying machines one moment and the subtle muscles of a smile the next. Michelangelo's David was not just a statue, it was a declaration that the human form, in its strength and beauty, was worthy of divine celebration. This human-centric spirit extended to the heavens. In Padua, Galileo Galilei pointed a new instrument, the telescope, at the night sky. What he saw shattered a 1,000-year-old cosmology. The moon had mountains. Jupiter had its own orbiting moons. These were not imperfections in perfect celestial spheres, they were other worlds. Here was direct, observable evidence that the Earth was not the immovable center of all things, but a planet in motion around the sun, a revolutionary and dangerous idea. While artists and scientists were redefining humanity's place in the cosmos, other restless minds were redefining its place on the map. In Portugal and Spain, navigators armed with improved ship designs, the astrolabe, and a relentless drive for trade and empire began pushing into the unknown. They were not the first great explorers, of course. Decades earlier, the Chinese Admiral Zheng had commanded a colossal fleet of treasure ships, sailing as far as East Africa on voyages of diplomacy and display for the Ming dynasty. But it was the European voyages that would irrevocably stitch the globe together. In 1492, Christopher Columbus, seeking a westward route to the Indies, stumbled upon a continent entirely unknown to Europe. A few decades later, Ferdinand Magellan's expedition, though he perished in the Philippines, achieved the first circumnavigation of the Earth, proving beyond doubt the planet's true scale and the interconnectedness of its oceans. These voyages were not mere journeys, they were collisions. The encounter between the Old World and the New triggered the Columbian Exchange, a biological transfer that reshaped life on every continent. To the Americas went horses, cattle, wheat, and sugarcane, transforming landscapes and diets. To Europe, Africa, and Asia came potatoes, tomatoes, maize, and chocolate, crops that would fuel population booms and change cuisines forever. But this exchange also carried invisible, devastating passengers, diseases like smallpox and measles, to which indigenous Americans had no immunity. The consequences were catastrophic, leading to a demographic collapse of staggering scale. This era, therefore, holds a profound duality. It was a time of breathtaking human achievement, of beautiful art and bold science that expanded the mind. Simultaneously, it was a time of brutal conquest and tragic consequence that remade the world through collision. Humanity's understanding of both the cosmos and its own planet was shattered and reassembled, setting the stage for a new kind of world, one of global connections and profound new questions about power, knowledge, and our place in nature. This new, interconnected world was hungry for power, and its thinkers were determined to find the source. A profound shift was underway, a move away from explaining the world through myth and tradition, and toward a method of relentless questioning and observation. This was the scientific revolution, and its champion was Isaac Newton. Sitting in his garden, the story goes, he watched an apple fall and asked a revolutionary question. Why did it fall straight down? His answer, published in his monumental work The Principia, was a single, elegant law of universal gravitation. He proposed that the same force pulling the apple to the ground also kept the moon in orbit around the Earth and the planets circling the sun. The universe was not a chaotic realm of spirits, but a magnificent clockwork governed by mathematical laws that could be discovered. This empirical method, testing ideas against evidence, became the new engine of understanding. 2 centuries later, another thinker applied this same rigorous logic to life itself. Charles Darwin, after a 5-year voyage aboard the HMS Beagle, observed the incredible variety of species, from finches on the Galapagos Islands to fossils in the ground. He proposed a simple, powerful mechanism: natural selection. Life was not static, but constantly adapting, with the traits best suited for survival being passed on. Humanity was not a separate creation, but part of the great branching tree of life. This was a second, earth-shattering revelation, placing us within nature, not above it. We had unlocked the laws governing the cosmos and the story of our own origins. But knowledge is power in the most literal sense. The understanding of physics and chemistry did not stay in the laboratory. It was about to be unleashed upon the world in iron and fire. The steam engine, first a clumsy pump for mines, was refined by inventors like James Watt into a reliable source of mechanical power. This single invention ignited the Industrial Revolution. For the first time in history, humanity broke its ancient reliance on muscle, wind, and water. Factories, dark satanic mills as the poet William Blake called them, began to rise, their brick chimneys belching smoke across the landscape. Machines powered by steam could spin cotton and weave cloth 100 times faster than a human hand. Cities, once centers of trade and government, exploded into sprawling metropolises as people flocked from the countryside for work. The world was connected by steam-powered trains and ships, shrinking distances and creating a global market. The acceleration was dizzying. In a single human lifetime, the pace of technological change went from a walk to a sprint. The glow of forge fires was replaced by the blinding glare of Bessemer converters mass-producing steel. The night, once lit only by flame, was now illuminated by gaslight and later the electric bulb. It was an age of astonishing invention, but also of profound dislocation. The rhythm of life, once tied to the sun and the seasons, was now governed by the factory whistle. The social consequences were immense, creating vast wealth for some and grueling, dangerous poverty for others in crowded tenements. And for the planet itself, this was a turning point. The burning of coal on an industrial scale began pumping carbon dioxide into the atmosphere at a rate the Earth had not seen for millions of years. The human enterprise, once a small thread in the biosphere's tapestry, was now a force powerful enough to alter the very chemistry of the air and the seas. We had harnessed the laws of nature, and in doing so, we began a grand, uncontrolled experiment with the only home we have ever known. The 20th century arrived as a paradox, a century of both brilliant light and unimaginable darkness. It opened with the promise of a new, modern age, only to plunge the world into the mechanized horror of the First World War, a conflict that shattered empires and introduced a terrifying scale of destruction. From its ashes rose new ideologies and a second, even more devastating global war, a total war fought across continents and oceans that culminated in the most awesome and terrible scientific achievement of all, the atomic bomb. The flash over Hiroshima announced humanity's newfound power to end its own story. The war's end did not bring peace, but a new kind of stalemate, the Cold War. This was a global standoff between two superpowers, the United States and the Soviet Union, fought not with armies on battlefields, but with spies, proxy wars, and a terrifying race to amass nuclear arsenals capable of destroying civilization many times over. Yet this same rivalry propelled us off the planet. The space race began with a simple beep, the signal from Sputnik, the first artificial satellite, circling the Earth in 1957. It was a shock that galvanized a generation. Just 12 years later, the world watched, holding its breath, as Neil Armstrong's boot touched the dusty surface of the moon. For a moment, the divisions of Earth seemed small against the backdrop of the cosmos. While rockets pointed skyward, a quieter revolution was unfolding on the ground. The room-sized, clunky computers of the mid-century, built for code breaking and calculations, began to shrink. The invention of the transistor, and later the microchip, allowed computing power to be packed onto a sliver of silicon. Machines that once filled entire buildings could now sit on a desk, then on a lap, and finally in the palm of your hand. This digital revolution changed everything. It gave us the personal computer, a tool that put unprecedented creative and analytical power into individual hands. And then we connected them. The Internet, born from a Cold War project to create a communications network that could survive a nuclear attack, evolved into a global nervous system. It dissolved borders of information, creating a world where a message could circle the globe in milliseconds, where knowledge from every library became accessible from a bedroom, and where new forms of community and commerce could spring up overnight. This digital web was the final thread in the tapestry of globalization. Container ships now moved goods across oceans with robotic efficiency, tying economies together into a single, interdependent network. Jet aircraft made the world a day's journey away. Cultures, ideas, and brands began to flow across the planet at light speed. The 20th century, therefore, stands as the most concentrated period of human transformation in history. It was a century that witnessed the very worst we are capable of and the very best. We glimpsed our capacity for self-annihilation and then reached out and touched another world. We built machines that could think and then wove them into a global brain. We emerged from its 100-year storm more connected, more knowledgeable, and more powerful than any generation before us, carrying all the promise and peril of that power directly into the world we live in today. That beep from Sputnik was more than a signal, it was a starting gun. The race to the stars was on, a frantic, high-stakes sprint between superpowers that would push human ingenuity to its absolute limit. The culmination came on a hot July day in 1969. Hundreds of millions of people around the globe gathered around flickering television screens, their eyes fixed on a grainy, ghostly image. They watched as a ladder unfolded and a figure in a bulky white suit descended. When Neil Armstrong's boot pressed into the gray lunar dust, he spoke words that echoed across history. That's one small step for man, one giant leap for mankind. For the first time, a living being from Earth stood on another world. The photographs those astronauts took on their journey home would change us forever. One image in particular, Earthrise, showed our planet as a fragile blue marble hanging in the black void, a single, beautiful oasis of life in an immense and empty sea. It was a perspective that no painting or philosophy could ever provide. We saw our home not as a collection of borders and nations, but as a whole, a tiny, precious island in the cosmic dark. But our exploration did not stop at the moon. We sent robotic ambassadors on grand tours of the solar system. The twin Voyager probes, launched in 1977, became our farthest-reaching scouts. They gave us our first close-up views of Jupiter's swirling storms and Saturn's glorious rings. Voyager 1, after completing its mission, turned its camera around for one last look. From 4 billion miles away, it captured a final image, a pale blue dot. Earth was just a single pixel of light, almost lost in the vastness. Carl Sagan reflected on that dot, saying, "Everything we've ever known, every human being who ever lived, every triumph and tragedy happened there on a mote of dust suspended in a sunbeam." That image humbled us, but it also connected us. We did not just look outward, we also built a home in the sky. The International Space Station is a marvel of global cooperation, a permanently inhabited outpost orbiting 250 miles above the Earth. For over 2 decades, astronauts from different nations have lived and worked together in microgravity, conducting experiments that teach us about biology, materials, and the human body's ability to survive in space. It is a shining example of what we can achieve when we work as one species. Meanwhile, our robotic geologists have been busy on Mars. Rovers like Spirit, Opportunity, and Curiosity have rolled across the rusty Martian landscape, drilling into rocks, analyzing soil, and sending back panoramic postcards from another world. They have found clear evidence that Mars was once a wet planet with rivers, lakes, and possibly even a northern ocean. Their mission is to answer the most profound question we can ask: are we alone? They are searching for the chemical building blocks or even the faintest fossils of ancient Martian life. To see the deeper universe, we had to get above the blur of Earth's atmosphere. The Hubble Space Telescope, launched in 1990, became our window on infinity. Its crystal-clear vision showed us galaxies in their infancy, nurseries where stars are born in glowing pillars of gas, and the catastrophic deaths of stars in supernova explosions. It helped us measure the expansion rate of the universe and confirmed the existence of dark energy. Then, in 2021, we opened an even more powerful eye. The James Webb Space Telescope peers into the infrared, seeing heat instead of visible light. It can look back over 13 billion years, capturing the faint glow of the very first galaxies that flickered to life after the Big Bang. Its first deep-field image was staggering, a patch of sky the size of a grain of sand held at arm's length, containing thousands of galaxies, each one an island of billions of stars. This is not just exploration, it is time travel. We are witnessing the cosmic dawn, watching the universe assemble itself. For billions of years, we were simply part of the cosmic story, shaped by its forces. Now we have begun to read the story for ourselves. We have touched another world, sent messages to the stars, and looked back to the edge of time. This is our new chapter, written not just in rock and bone, but in rocket fire and starlight. That pale blue dot is now a world transformed by its own inhabitants. We have entered a new geological epoch, the Anthropocene, where human activity is the dominant force shaping the planet's climate and ecosystems. Look at a satellite image of Earth at night, and you see the proof, a dazzling web of light tracing the outlines of continents, the glowing arteries of our global civilization. Megacities of tens of millions pulse with energy, connected by instant communication and global supply chains that bring fruit from one hemisphere to a supermarket in another in a single day. This is a level of connectivity and control unimaginable to any previous generation. Yet this same power casts a long shadow. Our industrial metabolism, burning fossil fuels that took millions of years to form, is altering the atmosphere in mere decades. The evidence is etched in ice. Core samples from ancient glaciers show carbon dioxide levels are higher now than at any point in the last 800,000 years. The planet is warming, and the effects are no longer subtle predictions, they are daily headlines. Ice caps are melting at an accelerating pace, not in centuries but in years. Sea levels are creeping upward, threatening coastal communities. Weather patterns are becoming more extreme, with intensifying hurricanes, prolonged droughts, and catastrophic wildfires. This is not a distant problem, it is a present reality reshaping coastlines, economies, and lives. Our dominance extends to the living world as well. We are in the midst of a sixth mass extinction, a rapid loss of biodiversity driven not by an asteroid, but by human actions, habitat destruction, pollution, and climate change. Species that evolved over millions of years are vanishing in decades, unraveling the intricate web of life that sustains us all. The split screen of our modern age is stark on one side, the brilliant innovation of a global society on the other, the profound consequences of its footprint. We have become a planetary force as powerful as the glaciers that once carved continents. This immense power comes with an equally immense responsibility. For the first time in the 4.6 billion-year history of our planet, a single species holds the future of the biosphere in its hands. Our brief 200,000-year human story is just a whisper in the deep time of the cosmos, yet our actions today will echo for millennia. The question we face is not one of technology, but of wisdom. Having unraveled the mysteries of the universe from the Big Bang to the double helix, can we now write a sustainable next chapter for our own fragile, beautiful world? Our story does not end with the challenges we have created, but with the choices we will make. Looking ahead across the next few centuries, the path of humanity forks in two starkly different directions. One road leads to a world of deepening crises, where climate disruptions and resource conflicts define our existence. The other road leads to a future where we have learned to harness our ingenuity, not just for growth, but for harmony. This second path is built on a convergence of technologies that are already taking shape today. Artificial intelligence, no longer just a tool for predictions, could become a planetary partner. Imagine AI systems managing the global energy grid in real time, balancing solar power from deserts with wind from the coasts, and directing surplus energy to produce clean hydrogen fuel. It could optimize agriculture down to the square meter, using sensors and data to grow more food with less water and land, healing ecosystems instead of depleting them. Meanwhile, advances in genetic engineering might move beyond medicine to help restore the natural world. Scientists are already exploring concepts like de-extinction, bringing back key species to revitalize lost ecosystems. In the future, we could engineer coral reefs to withstand warmer, more acidic oceans, or design plants that actively pull carbon from the atmosphere and lock it away in their roots. Our cities will transform from concrete jungles into living, breathing organisms. Picture vertical forests, skyscrapers covered in greenery that clean the air and house wildlife. Transportation will be silent and emissions-free, with autonomous vehicles flowing through smart tunnels and electric aircraft ferrying people between urban hubs. The very materials we build with will be alive or self-healing, and our homes will produce all their own energy from transparent solar windows and bioluminescent plants. But this bright vision is not guaranteed. It depends entirely on our ability to navigate the immense challenges right in front of us. Climate adaptation will be the great project of this century. Coastal megacities may need to build colossal seawalls or, more elegantly, learn to live with the water by constructing floating neighborhoods and restoring mangrove buffers. Managing fresh water will require a new global ethic, moving from wasteful consumption to a circular system where every drop is recycled and reused. The transition from fossil fuels must be rapid and total, powered by a worldwide mobilization of resources and political will akin to the effort that put humans on the moon. The most critical resource we must manage, however, is our own humanity. These powerful technologies come with profound ethical questions. Who controls a super-intelligent AI? How do we ensure genetic tools are used for universal benefit and not to deepen inequalities? The future we want will not arrive automatically through invention alone. It will be built through global cooperation, wise governance, and a shared recognition that the pale blue dot is our only home. The next chapter of the human story is being written now in our laboratories, our policies, and our daily choices. It is a story about whether we, a species born from stardust and shaped by evolution, can finally grow into our role as stewards of a world, and perhaps one day bring that stewardship to the stars. The stars are no longer just points of light in our stories, they are destinations. Our next logical step is to become a multi-planetary species, to ensure that the story of life, having begun here, does not end here. The first chapter of this new age is already being drafted, not in science fiction, but in the blueprints of space agencies and private companies. We are returning to the moon, but this time to stay. Plans for lunar bases focus on the moon's south pole, where permanently shadowed craters hold water ice, a treasure more valuable than gold. This ice can be split into hydrogen for rocket fuel and oxygen for breathing, turning the moon into a cosmic gas station and a proving ground for living off another world. From this lunar outpost, the true prize comes into focus, the rusty plains of Mars. Establishing a colony on Mars is the greatest engineering challenge humanity has ever faced. We would need to construct pressurized habitats to shield settlers from radiation and the thin, cold atmosphere. We would need to grow food in hydroponic farms under artificial suns, recycle every drop of water, and perhaps even begin the slow, centuries-long process of terraforming, of making Mars more Earth-like. These are not just shelters, they would be the seeds of a new branch of human civilization, evolving its own culture under a pink sky with two moons. The journey to Mars is one thing, but what about voyages to other stars? The distances are so vast that conventional rockets are useless. A trip to the nearest star system, Alpha Centauri, would take tens of thousands of years. The solution may be generation ships, colossal arcs that travel for centuries, where generations are born, live, and die during the voyage, their descendants finally arriving at a new world. Or we may develop revolutionary propulsion, like light sails pushed by powerful lasers, capable of reaching a fraction of light speed and completing the journey in a human lifetime. As we prepare to spread life, we are also listening intently for signs that we are not alone. Projects like SETI, the search for extraterrestrial intelligence, scan the heavens for any unnatural radio signal or laser pulse. New telescopes will soon analyze the atmospheres of distant exoplanets, looking for the chemical fingerprints of life like oxygen and methane. Finding even simple microbial life elsewhere would be the most profound discovery in history, telling us that life is a cosmic imperative, not a lonely accident. This grand expansion raises profound ethical questions. If we find a lifeless but habitable world, do we have the right to seed it with earthly microbes, beginning a new evolutionary story? Do we alter entire planets to suit our needs? And if we encounter another intelligence, how do we approach it? The act of leaving our cradle comes with immense responsibility, a duty to carry life forward with wisdom and care. This is the ultimate horizon of our 2-minute journey, the moment when the child of the stars looks up from its home planet and decides to build new homes among them. Our story, which began in a flash of light, may one day continue under alien suns. Even our solar system's grand architecture is not permanent. Billions of years from now, the steady, life-giving fusion in the sun's core will begin to falter. As it exhausts its hydrogen fuel, a profound change will ripple outward from its heart. The sun will start to swell. For a time, it will become a subgiant, growing brighter and hotter. Earth's oceans will boil away, the atmosphere will be stripped by the fierce solar wind, and our planet will be left a scorched, barren rock. But this is only the prelude. Entering its final act, the sun will balloon into a red giant. In a slow-motion cataclysm spanning millions of years, its outer layers will expand outward, cool to a deep crimson, and engulf the inner solar system. Mercury, the closest planet, will be the first to vanish, spiraling into the stellar atmosphere and vaporizing. Venus will follow, its thick clouds dissolving into the inferno. Earth's fate hangs in the balance, a question of celestial mechanics. Even if our planet's orbit expands slightly from the sun's lost mass, the intense heat and radiation will have long since sterilized it. It may ultimately be swallowed whole, or it may survive as a molten cinder orbiting within the star's tenuous outer envelope, a ghost world circling a dying heart. The outer planets will witness this transformation from a safer but still transformed distance. Mars will be baked, its remaining ice long gone. The asteroid belt will glow with reflected crimson light. The gas giants Jupiter and Saturn will find themselves in a strange new neighborhood. Their icy moons, like Europa and Enceladus, will thaw completely, their subsurface oceans boiling into space, their surfaces briefly becoming warm, watery worlds only to have that warmth turn to a scalding end. Their atmospheres will be seared by the increased heat, potentially stripping away layers of gas. Uranus and Neptune, the icy giants on the fringe, will finally feel a summer's warmth, their frigid methane atmospheres churning with new storms as their ices sublimate. This is the inevitable future written in the laws of physics. Our solar system, a stable clockwork for over 4 billion years, will be utterly remade. The red giant phase will not last. Eventually, the sun will shrug off its outer layers entirely, creating a beautiful, glowing shell of gas called a planetary nebula. At its center, all that will remain is the sun's incredibly dense, Earth-sized core, a white dwarf. This stellar ember will glow with residual heat for trillions of years, slowly fading into a cold, dark crystal. The surviving planets, now dark and frozen, will continue their silent orbits around this cosmic tombstone. This humbling vista of a swollen red sun filling the sky of a dead Earth is not a prophecy of doom, but a perspective of profound scale. It reminds us that all cosmic structures, from stars to galaxies, have a beginning, a middle, and an end. Our time here, and the time of our entire planetary system, is a brilliant but fleeting chapter in a story that spans eons beyond our comprehension. But even the death of our sun is a local event, a single light flickering out in a vast and still expanding cosmos. To see the true end of our story, we must zoom out to the grandest scale of all, the ultimate fate of the universe itself. For billions of years, the universe has been expanding, carrying galaxies away from each other like dots on an inflating balloon. This expansion is not slowing down, it is accelerating, driven by a mysterious force we call dark energy. The future of everything depends on the strength of this dark energy, and scientists have sketched out a few haunting possibilities. The most widely accepted scenario is known as the heat death or the Big Freeze. In this future, the expansion continues forever, growing faster and faster. Galaxies will first be pulled so far apart that their light can no longer reach each other. The night sky for any surviving civilization will become utterly, permanently black, empty of all other stars. Within each galaxy, star formation will eventually cease as all the gas and dust is used up. The last stars, small red dwarfs, will finally sputter out after trillions of years. All that will be left are the cold, dark remnants, black dwarfs, neutron stars, and black holes. But even matter itself may not be eternal. A theoretical process called proton decay suggests that over unimaginable timescales, perhaps 10 to the power of 34 years, the very protons that make up every atom could spontaneously disintegrate into radiation. If this is true, then all solid matter, every planet, every asteroid, every piece of cosmic dust, will slowly evaporate into a thin haze of particles and light. The black holes will be the last structures standing, but even they are not immortal. Through a quantum process at their edges, they slowly leak radiation, a phenomenon predicted by Stephen Hawking. Over eons so long the number has almost no meaning, even the most massive black holes will evaporate in a final, faint puff of Hawking radiation. The universe will then be a nearly perfect vacuum, an endless, dark, and cold expanse where the temperature approaches absolute zero. Occasional particles and photons will drift through the void, so far apart they will never interact again. This is the heat death, a state of maximum entropy where all energy is evenly spread out, all gradients have flattened, and no work can ever be done again. It is the ultimate silence. There is another, more violent possibility called the Big Rip. If dark energy becomes stronger over time, its repulsive force could eventually overcome every binding force in nature. First, galaxy clusters will be torn apart, then individual galaxies. As the acceleration grows exponentially, it would rip stars from their galaxies, then planets from their stars. In the final moments, hours or even minutes before the end, the expansion force would exceed the forces holding atoms together. Molecules, then atoms, then atomic nuclei, and finally the very fabric of space-time would be shredded. The universe would end not with a whimper, but with a catastrophic, instantaneous disintegration of all structure. These are not prophecies, but possibilities written in the mathematics of our best theories. They paint a profoundly humbling portrait of an end that makes even the lifespan of stars seem brief. Our entire cosmic saga, from the first flash of the Big Bang to the last thought of the last conscious being, is but a brilliant, fleeting spark in an unimaginably long and darkening night. This final mystery leaves us with a silent, awe-filled question. In a cosmos destined for such emptiness, what is the meaning of our brief, beautiful moment of light? From that single, hot point of infinite potential to the cold, dark possibilities of a distant future, we have raced across 13.8 billion years. We witnessed the first stars ignite, galaxies weave themselves into a cosmic web, and our own solar system coalesce from stardust. We saw life emerge on a tiny blue world, watched dinosaurs rule and fall, and marveled as a curious ape learned to walk upright, tell stories, and ultimately reach for the moon. We built civilizations, unlocked the laws of physics, and connected our entire planet with light and data. We now stand at a crossroads, holding the power to shape our world's future while peering back to the edge of time itself. This entire epic, from the Big Bang to the possible Big Freeze, unfolds on a timescale so vast it defies human intuition. In the grand calendar of the cosmos, if the Big Bang occurred on January 1st, all of recorded human history occupies the last few seconds before midnight on December 31st. Our entire species is a brand new thought in an ancient, ongoing story. Yet here we are, conscious of it all. We are the universe looking back at itself, trying to understand its own origins and its ultimate fate. That self-awareness is the most stunning miracle in this entire 2-minute journey. We are stardust that has become conscious matter that has begun to ponder its own existence. This makes our brief moment here on this fragile pale blue dot unspeakably precious. It is a gift of cosmic significance. So what do we do with this awareness, with this fleeting spark of light in the long cosmic night? The call to action is written in the story itself. First, cherish this moment. The fact that you are alive right now in a universe capable of producing life and mind is a statistical wonder. Savor the beauty of our world, the connection of human community, and the profound privilege of consciousness. Second, protect this chapter. We are the first generation to see our planet from space, to understand its fragility, and to recognize our impact. With our newfound power comes a profound responsibility to be stewards, to ensure this vibrant chapter of life continues for generations to come. And third, never stop looking up. The story does not end with us. Our curiosity is our greatest inheritance. Keep exploring, keep asking questions, keep pushing the boundaries of knowledge. Whether you gaze at the night sky with wonder, support scientific discovery, or simply share this cosmic perspective with someone else, you are participating in the next line of the human story. We are all part of this incredible, ongoing epic. What do you think the next chapter holds? Share your thoughts on this grand cosmic story in the comments below. If this journey through time resonated with you, please like this video and subscribe for more explorations into the mysteries of space and our place within it. Thank you for watching.